NASA just confirmed. Parker Solar Probe found something impossible. Right now, while you're listening to these words, something is happening that almost nobody on Earth is thinking about. It is smaller than a family car. It has no crew, no windows, no way to repair itself. At this very moment, it is racing through one of the most hostile environments in the entire solar system, at nearly 700,000 kilometers per hour. That is fast enough to travel from New York to Los Angeles in less than 20 seconds. It is not orbiting Earth. It is not heading toward another planet. It is not exploring deep space like Voyager. It was designed before artificial intelligence became part of everyday life, before reusable rockets transformed spaceflight, before most people had ever heard the phrase space weather. Every second, it flies through temperatures that would instantly destroy ordinary spacecraft. Yet, just a few centimeters behind its heat shield, many of its instruments continue operating close to room temperature. For decades, scientists believed one region around the Sun could only be understood from a safe distance. They were wrong. The researchers involved in this mission are careful with their language. They rarely use words like impossible or miracle. Instead, they describe what they measured as astonishing, unexpected, and in several cases, forcing scientists to rethink long-standing ideas about how our star works. Because in 2021, this spacecraft accomplished something no human-built machine had ever done before. It flew inside the Sun's outer atmosphere. This is the story of the Parker Solar Probe, and here is the part the headlines are not telling you. It is not only what Parker discovered inside the Sun's corona, it is what those discoveries mean for the satellites above your head, the power grids beneath your feet, and every technology on Earth that depends on understanding our unpredictable star. It is also what Parker is still doing right now, years after that historic flight, as it continues making ever closer passes around the Sun. And finally, it is what scientists hope to learn during its remaining planned encounters, observations that could reshape our understanding of the solar wind for decades to come. Stay with me, because by the time this is over, you will never look at the Sun the same way again. Every scientific mission begins with a question. The Parker Solar Probe began with one that frustrated astronomers for more than half a century. The question sounded almost backwards. Why is the Sun's atmosphere hotter than the surface that creates it? At first, that may not sound strange. But imagine standing next to a campfire. The closer you move toward the flames, the hotter it becomes. Now imagine walking away from that fire, and instead of cooling down, the temperature suddenly rises thousands of times higher. That makes no sense. Yet that is exactly what astronomers found when they studied the Sun. The visible surface of the Sun, called the photosphere, reaches about 5,500 degrees Celsius. But the faint outer atmosphere surrounding it, the corona, can exceed 1 million degrees Celsius. In other words, the atmosphere is hundreds of times hotter than the surface beneath it. For decades, researchers knew this measurement was real. They simply could not explain why. Some suspected magnetic fields. Others proposed invisible waves carrying enormous amounts of energy. Still others believed countless tiny explosions were heating the corona continuously. Each explanation solved part of the puzzle. None solved all of it. The problem was simple. Every telescope on Earth looked through millions of kilometers of glowing gas. Even space telescopes had the same limitation. They were watching from the outside. It was like trying to understand the inside of a hurricane while viewing it from orbit. Eventually, one scientist suggested something that sounded almost impossible. Instead of watching the Sun from a distance, why not fly directly into its atmosphere? For years, the idea remained little more than a dream. The engineering simply did not exist. Electronics would fail. Solar panels would melt. Communication systems would collapse. No spacecraft had ever survived such an environment. Then, one physicist kept asking the same question. What if technology eventually caught up? That physicist was Dr. Eugene Parker. Long before the spacecraft carried his name, Parker transformed solar physics by proposing that the Sun continuously releases a stream of charged particles flowing outward through the solar system. Today we call that stream the solar wind. When Parker first introduced the idea in 1958, many scientists doubted it. Years later, spacecraft observations confirmed he had been right. His work fundamentally changed our understanding of the Sun. But one mystery remained unsolved. What actually happens close enough to the Sun for that solar wind to begin? There was only one way to find out. Someone had to go there. For thousands of years, The sun was something humanity could only observe from a distance. Ancient civilizations tracked its movement across the sky. Modern astronomers built larger telescopes. Space agencies launched satellites above Earth's atmosphere. Every generation improved the view. None of them crossed the boundary. That changed in 2021. Not because the spacecraft landed on the sun, and not because it flew through flames. It crossed an invisible frontier, a frontier created not by rock or gas, but by physics. To understand why that matters, imagine standing beside a fast-moving river. Near the riverbank, you can still swim against the current, move farther out, and eventually the water becomes so fast that no swimmer can make progress upstream. Space around the sun behaves in a surprisingly similar way. The sun is constantly releasing the solar wind. This wind is not made of air. It is made of charged particles, mostly electrons and protons, streaming away from the sun in every direction. Close to the sun, something remarkable happens. The sun's magnetic field is still strong enough to control that flowing plasma. The particles remain connected to the sun's magnetic field lines. Scientists call this region subalphenic. Farther away, the solar wind becomes so fast that it breaks free. The magnetic field can no longer dominate the motion. From that point onward, the solar wind effectively escapes into interplanetary space. The boundary between those two regions is known as the Alphane critical surface. For decades, astronomers believed it existed. Mathematical models predicted it. Observations hinted at it. But nobody had ever crossed it. Nobody knew exactly where it was. Nobody even knew whether it formed one smooth shell around the sun. The only way to find out was to go there. In December 2021, NASA announced that Parker Solar Probe had done exactly that. The spacecraft crossed inside the Alphane critical surface during a close solar encounter earlier that year. In simple language, humanity had entered the sun's atmosphere for the first time. Notice what NASA actually announced. Not that Parker had landed on the sun, not that it had discovered a hidden object, not that physics had broken. The achievement was no less remarkable. For the first time, scientists were making direct measurements from inside the corona instead of observing it from millions of kilometers away. That difference is enormous. Imagine trying to understand a rainforest by looking at satellite photographs. You can see the forest, you can estimate its size, but you cannot hear the insects, you cannot measure the humidity, you cannot feel the wind. Walking into the forest changes everything. Parker had finally walked into the solar rainforest. Many earlier models pictured the corona as relatively smooth, complex, certainly, but still broadly continuous. Instead, Parker found something much more structured. The boundary wasn't fixed. It wasn't perfectly round. It wasn't located at one exact distance from the sun. Instead, it rippled, folded, shifted. As solar conditions changed, the boundary itself moved. Sometimes Parker crossed into the corona, then back out again, then inside once more. Imagine flying through clouds where the cloud bank itself is constantly rising and falling. That is much closer to what Parker experienced. Researchers had expected complexity. The level of complexity surprised many of them. Even today, scientists continue refining models because of these direct measurements. Long before entering the corona, Parker had already noticed something unusual. The magnetic field kept flipping direction, not permanently, briefly, suddenly, again and again. Scientists call these events magnetic switchbacks. Picture a flag blowing steadily in one direction. Then, for just a moment, a strong gust snaps the flag backward before it resumes its original motion. That is roughly what Parker detected in the magnetic field. The changes happened rapidly, over and over. Earlier spacecraft had seen hints of switchbacks much farther from the sun. Nobody knew where they formed. Nobody knew whether they were created during the solar wind's journey, or whether they originated much closer to the sun itself. Parker finally carried the instruments close enough to investigate. As Parker flew deeper into the corona, scientists noticed something important. Many switchbacks appeared connected to magnetic structures rooted near the sun's surface. That suggested at least some of them begin much closer to the sun than many earlier models proposed. Exactly how they form remains an active area of research. Researchers continue testing different explanations. Some involve magnetic reconnection, others involve plasma waves. Still others suggest multiple mechanisms working together. That uncertainty is not a weakness. It is exactly how science progresses. Real discoveries often answer one question. only to reveal 5 more. One lesson became increasingly clear. The sun is not quietly shining. It is constantly moving, constantly reshaping itself. Its magnetic field twists, loops, breaks, reconnects. Plasma surges outward. Invisible waves travel through its atmosphere. Gigantic eruptions occasionally launch billions of tons of material into space. Most of this activity never reaches Earth in dramatic ways. But some of it does. Powerful solar storms can disturb satellites, interrupt radio communications, increase radiation hazards for astronauts, even affect electrical systems on the ground during particularly intense events. That is why understanding the corona matters. This mission was never simply about satisfying curiosity. It was about learning how our nearest star behaves before its activity reaches our planet. And Parker had now provided scientists with their first direct measurements from inside that environment. Yet perhaps the biggest surprise wasn't a single dramatic discovery. It was something more subtle. The closer Parker approached the sun, the more complicated the sun became. Not simpler, not more predictable, more intricate. And that realization would influence nearly every new model researchers developed afterward. For more than 60 years, scientists had agreed on one basic fact: the solar wind exists. Every second, the sun throws enormous numbers of charged particles into space. Those particles sweep across the solar system. Eventually, they reach Earth. They shape the protective bubble surrounding our planet. They interact with Earth's magnetic field. They help create the auroras near the poles. But one deceptively simple question remained unanswered. Exactly where does that wind begin? That sounds like asking where rain begins inside a cloud. The closer you look, the harder the answer becomes. Parker was finally close enough to investigate that question directly. And what it found suggested that the solar wind is not produced by one simple process. Instead, different regions of the sun appear to contribute in different ways. Fast solar wind often emerges from coronal holes, areas where magnetic field lines open outward into space. Other portions of the solar wind appear connected to more complicated magnetic environments. Researchers are still working to understand how these sources interact. Again, the important point is not that Parker solved every mystery. It didn't. The important point is that, for the first time, scientists could compare decades of theoretical models with direct measurements from inside the region where those processes begin. That is an extraordinary scientific milestone, and Parker was only getting started. Every time Parker's solar probe completed another orbit, the mission team asked the same question: did everything survive? Because every close pass around the sun pushed the spacecraft beyond conditions that had never before been experienced by any human-built machine. The difference between one orbit and the next was not dramatic to the eye. There were no explosions, no cinematic moments, no last-second rescues. Instead, there were numbers, temperatures, voltages, magnetic field measurements, particle counts. Every successful pass meant one thing: the spacecraft was still healthy. And every successful pass also meant something even more important. Humanity had gathered another collection of measurements from a place that had never before been explored directly. Most spacecraft follow predictable routines. Parker does something unusual. It repeatedly breaks its own records. Each carefully planned flyby of Venus changes the spacecraft's orbit. Not by much, just enough. The result is that Parker falls a little closer toward the sun with every major encounter. As the orbit shrinks, its speed increases. By the mission's later encounters, Parker became the fastest human-made object ever built. That speed is difficult to imagine, so think about it another way. A commercial passenger airplane travels at roughly 900 kilometers per hour. Parker moves hundreds of times faster, fast enough to circle Earth in only a few minutes, if it could somehow fly at that altitude. Of course, it cannot. It is racing around the sun instead. That incredible speed is not for show. Without it, Parker could not remain in the orbit required to investigate the corona. The closer the spacecraft moves to the sun, the stronger the sun's gravity becomes. The faster Parker must travel. Physics leaves no alternative. Long before Parker launched, scientists knew that tiny dust particles fill much of the solar system. Fragments from asteroids, comets, ancient collisions. These grains are everywhere. Sunlight reflects from them. Spacecraft occasionally strike them. Telescopes detect their faint glow. But what happens extremely close to the sun? That question remained uncertain. Many researchers expected the intense heat to destroy dust particles before they reached the innermost regions of the solar system. Exactly where that happened was unknown. Parker offered a unique opportunity to investigate. As the spacecraft moved inward, its instruments detected evidence consistent with a region where dust becomes dramatically less abundant. Scientists sometimes refer to this expected region as a dust-free zone or dust depletion region. The observations continue to be studied. Researchers are still refining exactly where the transition occurs and how complete that clearing may be. Again, notice the pattern. Parker rarely provides simple yes or no answers. Instead, it replaces assumptions with measurements. That is how real science advances. Every so often, the sun releases enormous bursts of energy. Some involve brilliant flashes known as solar flares. Others launch vast clouds of plasma called coronal mass ejections, often shortened to CMEs. A large CME can contain billions of tons of charged material. Once released, it travels outward through the solar system. If Earth lies in its path, the effects may range from beautiful auroras to disruptions in satellites, navigation systems, radio communication, and electrical infrastructure. Scientists have studied these eruptions for decades, but almost always from far away. Parker changed that perspective. Instead of waiting for eruptions to expand across space, the spacecraft observed the environment much closer to where those events begin. That proximity allows researchers to compare models with direct measurements of magnetic fields, plasma behavior, and energetic particles. It does not mean Parker sees every eruption, nor does it mean every eruption behaves the same way. The sun remains enormously complex. Researchers continue analyzing Parker's observations to better understand why some eruptions become major space weather events, while others fade with relatively little consequence. One expectation scientists often have is that moving closer to a phenomenon will make it easier to understand. Sometimes that happens. Parker has shown the opposite can also be true. The closer the spacecraft approaches the sun, the richer the magnetic environment becomes. Field lines twist, reconnect, separate, merge again. Different streams of plasma overlap. Waves move through the corona. Particles accelerate. Some observations match existing theories remarkably well. Others require adjustments. Still others remain difficult to explain completely. That honesty matters. Scientific progress is not measured by how quickly mysteries disappear. It is measured by how accurately observations replace assumptions. Parker has already accomplished that repeatedly. But perhaps the mission's greatest contribution is not any single measurement. It is the realization that the sun's atmosphere is even more dynamic than decades of remote observations had suggested. Sometimes, the most important scientific result is discovering what is not there. Popular headlines often suggest space missions uncover hidden worlds, mysterious structures, or impossible objects. Reality is usually more interesting, because reality survives careful testing. Parker Solar Probe did not discover an object hiding inside the sun. It did not overturn the laws of physics. It did not reveal that everything astronomers believed was wrong. Instead, it refined our understanding. That may sound less dramatic. In science, it is often far more valuable. Every accurate measurement becomes another piece of evidence. Each new dataset strengthens some theories, weakens others, eliminates ideas that no longer fit the observations, and sometimes reveals questions nobody had thought to ask before. That is exactly what Parker has done. Researchers now possess measurements collected from inside the corona itself. Measurements that simply did not exist before 2021. Future scientists will spend years, perhaps decades, studying this archive. Some conclusions have already emerged. Others will require patience. That is how discovery works. Even after entering the corona, scientists continue investigating several fundamental mysteries. How exactly is the corona heated to temperatures exceeding 1 million degrees? What combination of magnetic reconnection, plasma waves, and other processes supplies that energy? How are magnetic switchbacks generated? Why do some disappear while others persist? What determines whether a solar eruption grows into a major space weather event? How do different regions of the sun contribute to the fast and slow solar wind? Parker has dramatically improved the evidence available to answer these questions. But researchers still cannot fully explain every observation. That is not disappointing. It is exciting. Because unanswered questions are what drive the next generation of missions. Unlike historic missions that ended decades ago, Parker Solar Probe is still producing science. With each carefully planned solar encounter, new observations return to Earth. Mission teams compare them with previous passes. Patterns become clearer. Unexpected details emerge. Every orbit adds another chapter. Every dataset helps refine models that may one day improve space weather forecasting. That matters more than many people realize. Modern civilization depends on technology orbiting above Earth. Satellites, navigation, communication, weather monitoring, scientific research. Understanding our nearest star is not merely an academic exercise. It is increasingly part of protecting the technological systems that modern life depends upon. It is tempting to think of great space missions as single moments. Apollo 11, Voyager's flybys, the first image from a new telescope. Those moments matter, but they are only the visible peaks. The real work happens quietly. Orbit after orbit, measurement after measurement. That is exactly how Parker's solar probe is changing solar physics. Every close approach adds another layer of evidence. Every stream of particles, every change in the magnetic field, every plasma wave, each one becomes another clue. One observation by itself rarely changes science. Thousands of observations can. That is why Parker was never designed to answer only one question. It was designed to build a library that researchers around the world will continue studying long after the spacecraft has completed its closest encounters. There is another remarkable part of this story. It begins with a scientist who almost saw his life's work rejected. In 1958, physicist Dr. Eugene Parker proposed that the sun continuously releases a stream of charged particles flowing through the solar system. Today, we call it the solar wind. At the time, many scientists were skeptical. The idea challenged prevailing assumptions. Eventually, observations confirmed that Parker had been right. Decades later, NASA made an unprecedented decision. The agency named a spacecraft after a living scientist. It was the first time NASA had done so for one of its flagship science missions. And when the Parker Solar Probe launched in 2018, Eugene Parker was there to witness it. He was 91 years old. Very few scientists ever see a spacecraft carrying their name. Even fewer live long enough to watch it begin answering questions they first asked more than half a century earlier. That is one of the quiet human stories behind this mission. Science often moves slowly. Sometimes an idea proposed in one generation is tested by the next. Sometimes the answer arrives 60 years later. One lesson appears again and again throughout the history of science. There is only so much you can learn from a distance. Galileo pointed a telescope toward Jupiter. Suddenly, the solar system looked different. Spacecraft flew past Pluto. Suddenly, it was no longer a blurry point of light. The James Webb Space Telescope observes galaxies that formed billions of years ago. Again, our understanding changes. Parker belongs to that same tradition, not because it discovered magic, not because it overturned physics, but because it replaced assumptions with direct evidence. For decades, researchers built careful mathematical models of the corona. Many of those models proved remarkably accurate. Others required adjustment. Some continue to evolve today. That is exactly what good science is supposed to do. Every observation strengthens our understanding, or tells us where it needs to improve. Parker has done both. It is easy to think of the sun as something constant. It rises. It sets. It has done so for every human who has ever lived. From Earth, the sun appears calm, almost permanent. But Parker reveals another reality. The sun is active, dynamic. Its magnetic fields are constantly changing. Plasma flows in every direction. Invisible storms move across millions of kilometers. Most of that activity never affects your daily life. Occasionally, some of it does. Large solar storms can influence satellites, radio communication, navigation systems, and power infrastructure. The better scientists understand those processes, the better they can improve forecasts of space weather. No mission can eliminate uncertainty completely. Nature rarely allows that. But better measurements almost always lead to better predictions. That is one reason Parker's work extends far beyond academic curiosity. Looking ahead, Parker Solar Probe is expected to continue operating through its planned sequence of close solar encounters, gathering additional measurements as its mission progresses. Engineers will continue monitoring every subsystem. Scientists will continue comparing new data with previous passes. Research papers will continue appearing. Some will answer existing questions. Others will introduce entirely new ones. That is the nature of exploration. Every frontier reveals another frontier beyond it. Long after Parker completes its mission, its data will remain. Graduate students not yet born when the spacecraft launched may one day analyze measurements collected during these historic encounters. That may be the mission's greatest legacy, not simply what it discovered today, but the discoveries it will enable decades from now. So what does all of this actually add up to? A spacecraft no larger than a small car, a launch in 2018, a historic crossing in 2021, an 11.4-centimeter heat shield standing between success and destruction, a journey that carries a human-made machine to within roughly 6.5 million kilometers of the sun's visible surface. Those are remarkable numbers, but they are not the real story. The real story is that humanity finally stopped looking at the sun only from the outside. For the first time, we stepped inside its atmosphere. We measured, we listened, we learned, and perhaps most importantly, we discovered how much remains unknown. Because the closer Parker moved toward our nearest star, the more complex that star became. That is one of science's greatest lessons. Every answer opens another question. Every discovery reveals another mystery. And with hundreds of billions of stars spread across our galaxy alone, it is genuinely worth wondering what other surprises are still waiting to be understood. If you enjoy documentaries grounded in real published research, rather than exaggerated headlines, make sure you subscribe and turn on notifications. Because the universe does not need exaggeration. Reality is already extraordinary.